Recording in progress.
Hey everybody, welcome back. We are to some applications using the integral. And I want to start with, we're at section 3.7 here. We have a demand curve and a supply curve. And they're not always straight lines. You can see in the picture here, they're nice, pretty curves. And I want to interpret this graph for us. A consumer surplus means that there is more demand than there is product out there. And as a business, if I have a product, but I've run out of the product and people still are demanding it, that means I'm losing money because I haven't made enough of the product to sell them to make the maximum amount of money that I can. The other side of that is if we have a producer surplus, and what that means is, what if I make too much of a product and then it doesn't sell? Well, then again, I'm losing money because I've spent money making extra product, but I'm not able to sell it. And so that forces me to either have to drop the price, either possibly even below the price that it cost me to produce it, just to get some of the money back. But ideally, we want to hit what's called an equilibrium price. That is that sweet spot right there. And you can see the Q star, P star. And that's what we're shooting for. And then we want to use those values to come up with what's called the consumer surplus and the producer surplus. And we have some fancy formulas here. We have the consumer surplus and we have the producer surplus. And when we add the two together, we should get the total gains from trade. So let's go ahead and start with our example here. And I'm going to go ahead and take these values and put them on a separate sheet of paper so that we can write them out. So here we go. So for our first example, we have that our demand curve is 1620 over root x, and our supply curve is 5 times root x. And they start out, they don't label it part A, but I'm going to call it part A because there's a couple parts here. It says find the equilibrium quantity, meaning how many items or units do I need to produce that will optimize, meaning I will sell all of them and I will won't have any left over and there won't be any more demand is the idea. So basically, where are these two functions equal to one another? I'm going to go ahead and multiply both sides by root x and divide by 5. Root x times root x is just x. And 1620 divided by 5 is going to give me 324 items. And that is my equilibrium point. There's my first answer there. And I'm going to turn off Do Not Disturb. Sorry about that. And then part B says, we're going to actually do some calculus here. It says find the consumer surplus. Now the consumer surplus and we use x in this case, minus p hat, or not hat, but star times q star. And what we have found with our x value here is that this is my q star. And we have not found our p star. What I'm going to do is I'm going to plug that x value into either d of x or s of x. It doesn't matter which one. The point is we should get the same value regardless. So I'm going to plug it into the top one. And see what we get. So 1620 divided by the square root of 324. And this is my p star. So our equilibrium point is 324, 90. And again, this is my q star and this is my p star. So let's go back to our problem here. We're going to go the integral from 0 to q star, which in our case is 324. D of x, which is 1620 over root x, dx, minus p star, times Q star. And I'm going to rewrite all of this. I'm going to pull that 1620 out. I'm going to go the integral from 0 to 324. And it's going to become x to the negative 1/2 power minus, and let's see what 90 times 324 is. So I'm getting 29,160. 160. All right, I'm going to build this integral. I'm going to go kind of slow with it. So this is 1620. And using the power rule, I'm going to get 1 over negative 1/2 plus 1, x to the negative 1/2 plus 1, and I'm going to go from 0 to 324 in this case. And negative 1/2 plus 1 is 1/2. 1 over 1/2 is just 2. And 2 times 1620 is going to give me 3240. So 3240 x to the 1/2 power from 0 to 324. Oh, you know what I didn't write in? Let's move this a little bit. I didn't write in my minus 29,160. And root 324. So square root 324 is 18 times 3240. So I'm getting 58,320 minus 29,160. So so we are going to get $29,160. And that is our equilibrium quantity. I'm sorry, our consumer surplus at equilibrium. Kind of cool. So there is me optimizing my business. Let's move on to the next example. This one's going to be very similar, except we are going to be doing a supply function in this case. So we start with a demand function of 2420 over root x and a supply function of 5 root x. And we start out like we did before, finding the equilibrium quantities. So let's set the two equal to each other. So 5 root x equals 2420 over root x. Root x times root x is just x, and 2420 divided by 5 is 484. And here is my equilibrium. Oops, items. And now we want to find out what is the producer surplus. So I'm going to call this part B. And producer surplus, if we go back to our formula, is P star times Q star minus the integral from 0 to Q star of S of x dx. I mean, and I know on our notes it uses Q, but it all means the same thing in the end. All right, so we did not find P star, so we have Q star, and I'm going to again plug this into the demand function. Again, you know what? This one, let's plug it into the supply function. Just show you we're going to get the same value. It doesn't matter. So we get 5 times the square root 484. So we're getting 110. This is my P star. And again, this is my Q star. Again, I'm going to go ahead and plug that into our demand function as well. So 2420 divided by the square root of 484. And you can see we're getting the same value. So, and that's the point, is that that same value should work in both functions. In fact, that 484 should be the only number of items that will work for both the demand function and the supply function. Okay, now that we have both of those, so let me write it as a point. So 484 and 110 is our equilibrium point. So this is going to give me 484 times 110. So we are here. And again, this is just using the supply function. And this is going to give me, let's see, 484 times 110 is 52,240, 53,000, pardon me, minus 5. And this is going to be, that's x to the 1/2 power. This becomes 1 over 1/2 plus 1, x to the 1/2 plus 1 from 0 to 484. So 53,210. 1/2 plus 1 is 3/2. That becomes 2/3. And then this becomes x to the 3/2 from 0 to 484. Now I want to be clear, 0 to the 3/2 is just 0, so I'm not going to bother wasting my time with that. However, I am going to do 484 to the 3/2. 484 raised to the 3 divided by 2 power gives us 10,648. And let's see. So let's go 53,240 minus 10 times 10,648, all divided by 3. Let's see what our grand total is. So we're going to have to do some rounding off. We're going to get $17,746.67. And that is our producer surplus. No problem. Next up, I'm going to switch back to our regular notes so we can take a look. And so we did these two. Number 3, I'm going to skip. All right, so we are now to compound interest formulas, and compounding n times per year, we have our formula A equals P of 1 plus R over n to the nt power. We are more interested in the continuously compounded. That's the A equals P e to the RT power. And when t is positive, A of t is what we call the future value, meaning what it's going to be worth in the future. And if we want to go the other way, if we want to say, how much do I need to invest now so that later it'll be worth a certain amount of value, then we call that the present value. And that's when we're sort of looking backwards of how much did I need to invest to have this much in so many years. And we have our present value formula. And it is right here, where f of t is the continuous income function. Our examples that we're going to be doing, that's going to be a constant, meaning it's going to be specifically $11,000 every year. So it's just going to be a specific amount. In more complicated ones, of course, it becomes some function of time, meaning that continuous income is going to change over time. Maybe inflation is included, or some sort of natural disaster happens, or whatever the case is. But for us, it's just going to be a constant. And then we have the future value that we have there. I'm going to, again, move back to some blank paper so that we can work these problems out. And so we are to the next example. This is continuous income stream. And we have the accumulated present value of an investment over a 10-year. We're going to find the present value over a 10-year investment. There's a continuous money flow of, in this case, $11,000 per year. So again, that's a constant. So there's no function. The function of t is just where t isn't a factor. They give us the interest rate is 1.2%, so it's 0.012. And it's compounded continuously, which works for us. So our present value is going to be the integral. I'll write the general formula here, f of t e to the negative RT dt. And Finding this formula is not particularly complicated, but again, in our case, f of t is 11,000, r is the 0.012, and we're integrating with respect to t, so this is lowercase t. And so here is our actual integral for our present value. Now, if you remember before, numerous times I've done this, when we have e to the ax power, we end up with 1 over a, e to the ax plus c. So we end up with that extra 1 over a. The plus c won't apply to what we're doing because we have a definite integral in this case. But we're going to end up with an extra 1 over negative 0.012 when we integrate this. So I'm going to get 11,000 over negative 0.012 e to the negative 0.012 from 0 to 10. All right, remember e to the 0 power is 1. It's not 0, so the whole thing doesn't just go away, unfortunately. This becomes e to the negative. Now 10 times 0.012 is just 0.12. And e to the 0 is just 1. And so let's knock all of this out. So let's go e to the negative 0.012 minus 1 times 11,000 divided by negative 0.012. So I'm getting let me do this again. Something's just slightly off here. So second e to the negative 0.12 minus 1 times 11, 1, 2, 3, divided by negative 0.012. There we go. So I'm just comparing this to my notes. So this is going to be $103,656.27. And that is the present value, where it's gaining 11,000 every year. Kind of cool. In our last example, so a company is considering expanding their production capabilities with a new machine that costs $78,000. It has a projected lifespan of 9 years. So there's my T I'm going to compare to. They estimate that the increased production it will provide is about $9,000 per year of additional income. Interest or the rate is 0.7%, which is 0.007. And so they're asking, should the company buy the machine? So if we do all this, find out that the present value is more than $78,000, then yeah, we should buy the machine. Because $78,000 would be cheaper than having to pay every month or every year. Versus if it's below 78,000, then we should not buy the machine. So let's find the present value. There is our integral. And remember, when we integrate that, we're going to get that 1 over negative 0.007. From 0 to 9. And I'm going to figure out what 0.007 times 9 is. Okay, so this becomes negative 0.063 minus e to the 0, which is again just 1. And let's see what we get. So e to the negative 0.063 minus 1 times 9,000 divided by negative 0.007. And that is getting me about $78,501.25. So what's our answer? Should we buy it? So he should. So they should buy the machine. Since $78,000 to buy it is less than the $78,501.25 is less than that by $501.25. So it's going to be a better bargain to just buy the machine than it is to use it as presented. All right, I hope that helps everybody.